Happy Good Friday, and we're here. Looks like a beautiful day in April in Maryland. Um, just want to talk a little bit about uh, homework, what's going to be on the exam next week, and what's posted up on Canvas to help you prepare for the exam. I guess I'm looking here at our Canvas module, and this is the scattering part. And I have posted the solutions to the two tutorials for scattering. Remember, that's what's going to be the start of what will be on the exam that we're putting out next Wednesday. That'll be due next Friday. It's a take-home open book. Same rules as last time. Open book, open notes, open resources in terms of Wolfram Alpha, anything you want to Google, any papers you can find, any other instructors from other schools material, all good. The one thing you cannot do is consult with another person, and that would include both an online tutorial system that has an online tutor that you can talk to, or anybody face-to-face, or corresponding by email or anything like that to get help. It has to be your individual work. But if you can find a published resource on the web, you can find a published resource in the library, that's fair game. Any resources to do mathematics are, of course, all fair game as well. Right, so I'm starting to post my solutions. Anything in there is good for you. I've posted the Dirac notation and the matrices tutorial solutions. I haven't graded or posted the observable statistical interpretation, generalized uncertainty, or using Dirac notation, which I guess using Dirac notation was due Wednesday. I'll be getting to that this weekend. I have many papers to grade, and those tutorials are among them. If you haven't turned them in yet, now's the time, because once they're in and they're posted, they become worth less. I want to say one thing about homework 7, because I realized I was going through my solution again, that there is something missing that could lead you astray. And so let me pull up my solution here. If you look at problem 1, I think very straightforward. If you're doing more than multiplying a matrix times a vector and maybe the pre-multiplying by a broad dual as well, you're missing the point of how to find an expectation value. Let me zoom in on this. The second one, though, and oh yeah, you may notice all the tutorials were 2x2, and now we're giving you 3x3, right, on the homework. So it's the same thing, same mathematics. It's just a little bit different because you got a 3x3 instead of a 2x2. And hopefully, that won't be too big a deal for you. Here's my solution. Oh, there it is. I do want to point out on this guy right here, the Hamiltonian, you get a bunch of elements that are 0. Hopefully that makes the math a little bit easier. When you're looking at, I guess, the determinant, or is it when you're trying to get the eigenvalue, or is it actually when you go to get the eigenvector? I think when you go to get the eigenvector, you'll look and you'll go, okay, is it possible to have C equal to be A minus B? And that would kind of help you get an eigenvector. I want to just put a constraint on this problem that I didn't type in that is true. So make sure if you come to this step, and you should, that you realize that C here, that middle coefficient, that guy right there, is not equal to A minus B. Okay, if you make the C equal to the difference between the other two coefficients, A and B here, you'll get kind of a trivial solution for the eigenvectors. And so something else has to be 0. If you find yourself trying to set these two guys equal to 0 to make an equation work, something else has to be equal, or something else has to be 0. And so that's the one constraint. C is not equal to A minus B. All right. And I apologize for not typing that in when I wrote the problem. It doesn't say that here anywhere, but that is you'll go the wrong direction if you don't make that assumption. All right, any questions on that before I move on? All right, then I'll stop sharing. Well, first of all, I guess I'll put that thing away, and then I'll stop sharing Canvas, and I'll swap over here to what we were talking about. Zip back a couple slides to pull in what we've been doing and share that with you. All right, yep, got the green border, so that's what you're seeing. And now let's go to presenter view here. And that way I can annotate, get our pictures out of the way because they get in the way of the video. I'm going to put them down here. And I just want to remind, well, I'll be going right there. It's funny. Let's back up a couple slides. Okay. And what we were doing, and, you know, it is a little bit of a redefining variables, functions over and over and over again. And so we're solving the time-independent Schrodinger wave equation using the separation of variable techniques. We recognize this is an eigenvalue problem, and in 3 dimensions in spherical coordinates, substituting in for that Laplacian is this big long monster, which physicists aren't going to teach you why that is. You have to go to a mathematician. Although in Griffith's E&M book, if you care to see why this comes to be in spherical coordinates, he does give you a justification in the appendix. In any event, we care that that is the Laplacian in spherical coordinates. We plug it in, and then the first redefining of variables is the wave function we're looking for, which we now should be firmly able to say is the energy eigenfunction or the energy eigenstate, where E is the energy eigenvalue. We swap it for its 2 separable functions, R and Y. Y is the spherical harmonic function, and R is only a function of the variable R, and Y, the spherical harmonic function, is only a function of theta and phi. And so we played with Y on, I guess, Monday and Tuesday of this week, the spherical harmonic function Y, and that tutorial is due at the end of the day today. I've already seen 1 or 2 of them turned in. It's not as challenging as some of the others. It's a little more straightforward. You have to do an integration though. Feel free to use Wolfram Alpha. You got to take some derivatives to show that a function is a solution to the separated equation for Y, which is right here, because that's the next thing I'm showing is we do the normal separation of variables technique, and we get an angular differential equation for Y and a radial differential equation for R, the 2 functions, Y and R, okay? And we pretty much beat up the Y equation. We didn't do a whole awful lot with it, quite frankly, other than say, hey, Legendre and a guy named Rodriguez figured out the solutions and a way to succinctly write the solutions, and we're just going to use their work. We're going to literally follow in the footsteps of giants here and just not try to solve it as they did back in the 1800s, but just to accept their answers. The radial solution, though, we've been working on, and we're going to spend a little bit of time developing a solution from that, because there are conclusions that come out of this solution to the radial portion of the differential equation that have physical significance, and we want to demonstrate them. Remember, a lot of our solutions will not have the arbitrary constant that we might want. So when we need to get that arbitrary constant, we normalize whatever the answer is, okay? And we had separated the normalization up into a radial part. And since in spherical coordinates, that is the volume element right there, R squared sine of theta, dr d theta d phi. Uh-oh, I may be breaking up here. Comcast gives me a little flash when my internet connection's a little shaky, and that I'm finding in my PHY322 class that they start chatting, is he breaking up? And the answer is yes. And then I stall for a little bit. It usually comes back. For all the money I pay Comcast, it should be a little better. But in any event, I can talk now, I think. The R squared piece and the dr get lumped with the R separable function, separation of variables function, and everything else, okay, so that goes with R, this, and this, which we call the solid angle differential. That is, when we normalize the Y piece, that's what we use, okay? And so that has to be how we separate the volume element in spherical coordinates into pieces, and we handle them one at a time, but that is the generally accepted convention. Okay, we were working with the radial equation, and if you remember, the separation constant was this guy right here, L plus 1, a little bit wacky, but in spherical harmonics, it fits with the way Legendre and Rodriguez indexed the solutions, which, if you look, are cosines and sines and things like that. Any event, makes a good index for us. And we keep changing variables in solving the radial equation. I'm going to do it at least, well, I'm going to change the function 2 more times, one right here and then a second time. And then I'm even going to switch from R to another variable rho. And so if you're kind of following this, we start out with the function R of little r, okay? And right now I'm going to shift it over to u, okay, as a function of r still, so that's good. We've only changed that, and this is how we're going to define u, and I think we did this last class. As we move through, I'm going to redefine this guy in terms of this other function, v will be the next function, and by the time I get to there, I'll have shifted r to another variable, which is rho. And at the end, we'll be solving this when we want it to get the u function. And then from that, we can figure out what the radial wave function is by reconstructing, putting it all back together. Stitching it all together is what I've heard some physicists and mathematicians refer that to. But if I can find u, I can get r. And if I can get v, I can get u, and then I can get r. And so that's how it works. And of course, I changed the variable from r to rho just to make it even more fun. In any event, if we do this, and we're trying to solve this differential equation, all I did in the next differential equation, I multiplied through by the r, so it shows up there and there, okay? But I make this substitution. Hopefully you can see why. The function r is often multiplied by either r or r squared variable, and it shows up that way. And so it just kind of makes sense to do that. And so I started with r, I took its derivative, I multiplied by its r squared. I'm doing that term right there, and then I take the derivative of that. And if you look, it simplifies out real nice. That goes right in there, and that's what I did right here. And so it's just a little easier. And then I just pushed the symbols around the page a little bit. Once I got rid of r here, well, I guess I had to get rid of r here and here as well. And so r is equal to u over r, and so that's why that shows up right there and right there, and everything else should be exactly the same. And then I just manipulated it around a little bit. Literally just push the symbols around in 2 slides right here, and I get to this equation at the bottom. And that has significance, I think, once we've made that substitution. The reason why is, if you look, this equation right here, this stuff that just kind of comes together, well, first of all, you see an eigenvalue equation. I have an operator. Where's my operator? It's right here, plus all of this, because all of that is operating on u, right? So all that stuff is operating on u. I just had to redefine the potential to be this, and then the operator really is the Schrodinger's time independent Hamiltonian operator. And so I'm solving that eigenvalue equation, which is what we've been working on all along here. I've just gone from the potential that we did like in an infinite square well, a finite square well, a simple harmonic oscillator, to this effective potential right here. Okay, so that's a significant step, I guess. We just remember that the function we're looking for, the eigenfunction we're looking for, is the energy eigenfunction psi. Right, and talking about how to normalize it, it is kind of convenient. What I just said about normalizing just becomes this new function u squared dr. Okay, and I think that's about where I cut off on Wednesday, kind of in review. And so now we've got this equation, and this thing right here is that V effective, only in place of the potential, I have actually put in what the potential would be for the hydrogen atom, where you've got a plus E, a proton at the nucleus, and a minus E charge out. And I don't want this to be seen as like a orbital mechanics kind of path, but this electron is living somewhere outside of the proton, and that's the effective potential right there that we're talking about. Okay, and as you might guess, we're going to redefine things because that's what we do. And so I think what I want to do here, first of all, is take this guy right here, and I want to multiply it by this in the form of 1. And, you know, I do stuff like that, and you have to do it with foresight. You have to be looking ahead, because I think if you do that, and then you redefine one thing that we've done before, this kappa, okay? And then something we're going to talk about before, I'm going to define everything that's over here to be row 0, set myself up. I said I was going to change R to row. This is going to be like row 0, just a bunch of constants, okay? I can write this term like I've done right here. It's 1 over kappa squared R with these constants, and I'm just going to eliminate them, and you can see write that as row 0. Okay, now just about this kappa, this is the same kappa we had when we were doing scattering problems, or finite square well. And I do want, it looks like it's a complex number, but remember, we're doing only bound states right now. And when you have a bound state, E is less than 0. So that E right there is a negative number. So this is it is a real number. Kappa is a real number, just like it was when we were doing scattering problems, okay? On the other hand, if we were free, then unstable internet again, I'll stall. If we're doing a free problem, then I guess E would be a positive number, it'd be greater than 0. Kappa would become complex. We usually call it K then, and that is the scattering wave number, and then we factor out the I, right? The minus I. The I is because it's square root of -1, so you factor out an I. So since we're going with kappa, we're saying this is real because we expect a bound state. We expect E to be a negative number, canceling that negative sign. Okay, and so that's kind of the notation. Nothing new there. That's exactly what we called kappa before. I guess the one degree of specificity we've added here is the mass we're talking about. Make no doubt about it. It is the mass of this electron out here. So you'll see me subscript E. Hopefully I didn't drop the E too often. Okay, anyway, I think every other term is staying the same. I got rid of the E here, bringing it over to here, and then that became 1 over kappa squared. And then I think I brought the E in here, and that got me a kappa squared in there as well, okay? And then I'm watching this middle term right here, and it just becomes that, okay? The next thing, and I promised you this, I'm going to get rid of R now. As a variable, R is going to change to row here, and that's how we're going to change R into row. We're going to multiply it by this kappa, okay? And so I think if I do that, let's see, if I'm going to write row as kappa times R, then this derivative right here, which was taken with respect to R squared, I think if I just, and this is a little sleazy, but it does work out this way, that guy right there can replace that right there, and it becomes that right there, okay? So I've simplified the form of the derivative on U, the second derivative on U, by making this row substitution, and then this derivative just becomes a simple second derivative, okay? Let's see. Let's see here. I guess what I have here in this middle term, I said all that's going to be row 0. So you can see why I wrote that as row 0 in the top. Okay, and then there is one of the kappas is in that set of constants, right? It leaves kappa times row, which is what I wrote right there. So that term with this substitution and that substitution becomes a whole lot simpler, doesn't it? And then I guess the last one, this just becomes row squared right here. And so by making these substitutions, I think I'm creating a simpler looking differential equation to solve, okay? And that's really all I've done. This is still the radial differential equation R. I've gone from R as a function to U as a function, but now I've also gone from the variable R to the variable rho, and I've made the differential equation less complicated looking, I guess, is the way to describe it. All right, it wouldn't be unhelpful right now to look at the hydrogen atom tutorial, which is what we're kind of going through right now, if you're following along, if you can open it up in Canvas, you don't have to necessarily print it out. If we were in class, I would have handed it out to you. But the reason is this is how the tutorial starts with this differential equation. I think that's line 1 on the tutorial that we're working on next is, okay, so let's say we've got this thing. You want to look at what I call the asymptotic solutions. And that is what happens when this variable rho, which is substituted out r, goes very big, right? And yeah, this is exactly how the tutorial starts right here, is with this differential equation. And we're kind of given a justification for how we're going to solve it here. And either rho or r gets really big, that's clearly asymptotic. We're thinking, okay, what does it do as r approaches infinity away from that nucleus in the center? And I think if rho or r goes to infinity here, this term gets really big, this term gets really big, those guys go away, okay, and you're just left with the second derivative of u with respect to rho squared is equal to, well, 1 times u. And that's a differential equation that hopefully you can solve by inspection. I would write it this way to make it look more recognizable, I guess, in form. But it's a second derivative, I guess, minus u is equal to 0. And it's one that we often have, just you put some constant right here, I don't know, and then it has this form right here of an exponential solution with a real exponent. Usually there'll be a c up here, but in this case, c is equal to 1, isn't it? So that's why there's no c up there. So that's your solution. But you might say, that's an incomplete solution. There should be its companion, another constant, and then e, if I made that one minus rho, there should be a plus rho as well, again with the constant being 1 out in front of that guy in the differential equation. If that's not familiar to you, go back and look at the handout I gave you on like the first week of class. It was called Quantum Mathematics or something like that. Let's see, Quantum Math Tips was the name of that. And this is one of the differential equations that you're just presumed to know. This has a negative sign here. If it has a positive sign, of course, you recognize it's sines and cosines. It's a slightly different differential equation. In this case, it's negative. And if we're missing this, the worksheet's going to ask you, well, why is that missing? What's your justification for throwing that away? And hopefully you'll say, well, we're in the case where rho is going to infinity. At infinity, that term blows up. And since we're in a Hilbert space, an L2 space, if you're a mathematician, these things have to be normalizable. That's why that goes away, right? Similarly, and I don't know if the right word is asymptotic here, but what happens when rho or r, because they're replacement variables, rho is just kappa times r, is going to 0? Well, in that case, I guess, if that goes to 0, well, we're going to focus on this guy because that must be the biggest term, right? So we're just going to focus in on that guy. I mean, that guy's big too, but this guy's even bigger as this thing gets small because it's going to 0 much faster. And I didn't know this. And so you're going to show that this is a solution by plugging it back in. It's not one that I have known, memorized. I suppose if I worked on it, I can figure out a technique to solve for you. But what you're going to do to check to see if this is actually a solution, and are you going to have a companion with it? Yeah, it's actually one of 2 pieces. Just like there's another piece to this guy, there also is a solution here that is minus L minus 1. Both of those are solutions. And so you're going to plug u right in there. You're going to take the second derivative right in there and see, is this indeed a solution? And hopefully you realize if L is going to 0, then this guy is going to blow up. Whereas this guy won't, right? Because minus, is that right? I want to say that. All right. Yeah, I do want to say that because remember, is there a rho in there? There it is. Rho to the minus L minus 1. Probably breaking up right now again. Sorry about that. Comcast, I pay you way too much money. That would be 1 over rho to the plus L plus 1. And as L goes to 0, I think this thing's going to get pretty pretty big, and so we're going to make that guy go away. Okay, and so that's the thing, but you're just going to check to make sure that that solution works. Okay, yeah, and make sure it does. Did I write the right answers, the right solution? Yeah, I did. Okay, and by the way, those are steps 1 through 6 on the tutorial. It's basically differential equations, and the fact that these things need to be finite and normalizable at all points. Okay, so that's the steps 1 through 6 on the hydrogen atom tutorial, which will be due on Monday, by the way, just if you're keeping track here. That's when I've set it up. It's not a particularly long problem. There is some stuff that we're going to be talking about here that is kind of important to it, but I think that's doable by Monday. Now, the whole point of looking at these asymptotic solutions, and again, I'm not sure that's the right word for when R or rho is going to 0, is to motivate the next change of variables we want to do in our chain, where we're going from R, actually change of functions, to U. And now I want to introduce this third function that I promised you, and that's this function v, which, okay, this was a function of little r. This, I guess, was a function of little r for a while, but then became a function of rho. Oops, that's a u of rho. And now we're going to introduce a function v, which is a function of rho, because we can peel off the two asymptotic parts of the overall solution. And this is as a function of rho. So this is a new math function v here. Okay, and we peeled off the two asymptotic pieces, and so this is independent of that, I guess. And there's a motivation to change the variables again. Hopefully it gets us to something that we can try to solve for v, and then we slap on these two guys and we get u, and then of course we multiply or divide u by r and the variable r, and that gets us back to the function r, which is the radial part of the eigen function for the energy eigenvalue psi, which is our wave function. Okay, and once you do that, I guess our goal then will be not to solve for u, but to solve for v, and hopefully be able to reconstruct back there. Now, the math here is not contained in your textbook. I felt obliged to take you from one step to the other because you go from tutorial problem 6 here that is pretty well straightened out. And then when you go into 7, we just jump to the new differential equation that is v instead of u, and nothing fills in the blanks, and the textbook's no help either. And so I want to fill in that gap with the missing math. Okay, and I suppose if we believe that this is u here, as a function of this new function v that I'm going to replace it with, it's a second substitution, having stripped off the two asymptotic solutions we think are pretty believable from steps 1 to 6 of the tutorial, and maybe just what I just said right here, here and now. If I take the first derivative of that guy and push on it, du d rho becomes this term right here. Okay, and I've used the product rule to get it, because you can see I got a rho here, I got a rho here, and v is a function of rho. And hopefully you realize the product rule for 3 things is, let's see, what order did I do them here? I did the derivative of the first term, which brings down an L plus 1 times the second and the third. Okay, and then plus the first and the third times the derivative of the second. The derivative of the second brings down that negative sign. And then the derivative of the third times the first and the second is just that guy. And so then it was just a matter of doing simplification, and I get this as the derivative. It's tedious, but it's there. It's a product rule of 3 things that are a function of v. That's inconvenient, but you just handle them like you would a product rule of 2 things that are a function of rho, I guess, when you're taking the derivative with respect to rho. The second derivative, though, I'm giving you the answer here, and I want to show you the work, and you can review it at your leisure if you want. It is just calculus, so I'm going to escape out of here, hopefully. escape out of there. Yeah, discard those annotations. They'll be gone when we come back. And I want to show you where that work is in Canvas. So I'm going to go back to the Canvas webpage and share that with you as soon as, all right, your screen, you have to stop the share and share with you Canvas. And this is just so that you can pull it up, Google Chrome. Yep, there's Canvas. Share that. And of course, I've left you with the homework 7, which is due next Wednesday. And I would recommend you do before we, before you try to do the take-home exam. Okay, and so let's go back, come all the way down to spherical harmonics. And then I put radial equation steps is the name of the document, and it's right there. Okay. Kind of tedious to, I would download it. And so there it is in Canvas, so you know where to find it. I'm going to close that out, which should stop sharing. And instead, I'm going to share the PDF, the Adobe Acrobat with you. And so there's the work. I don't know why it's highlighted in blue. There it is. We just left off taking the first derivative, okay? And now I got to get the second derivative. Those are all the steps that get me to the second derivative, okay? And then I'm going to rearrange them as the textbook does, making these substitutions that we've talked about. The row 0, getting rid of u here already. There's what rho is, there's kappa, and this is the radial equation. And in your textbook, this is equation 4.6, my equation that gets rid of u in favor of v in my 2 asymptotic solutions, okay? And then we get down, he goes right down to equation 4.61. You can see there's nothing in between there to speak of. Does he show any work at all? Yeah, he does show 2 steps of algebra. I think it's about a page worth of algebra right there. And if you care to see how it works out, check my math. I think we're good to go right there. And there is the radial equation, okay? That is now a differential equation in V. I've only got V as opposed to the differential equation for the radial equation, which was U. And this is the guy we're ultimately going to solve. And there's a lot of pushing symbols around the page. I'm not sure how significant actually going through the math here in a Zoom session is important. But you should take a look at it. And at the end of the day, I guess you got to believe that. Let me open this up here. That I get to the second derivative of u. Right here, so that I can substitute that up in there. I've got the u original function. I can substitute it right in there, and I can get rid of things that can be gotten rid of, and I get a much more simplified differential equation. Yeah, not much more simplified, but it's got a lot of these constants in it. And this equation right here is where you start. Come on, Comcast, come on back. This equation right here starts problem 7 on the tutorial. So everything I've shown you right there gets you from step 6 out to the new differential equation in V, which is our goal to solve, okay? And so that's the guy, just brought that to the other side of the equation, so it comes right in there, and that's the differential equation we're solving. All right, and how do we solve that thing? Well, the answer is a power series solution. Go figure. And this is what the tutorial walks you through. And I've done like the first step. And there's V. I'm going to say it is a constant that varies with the exponent of rho. And so this would be like rho 0 plus rho, I'm sorry, no, it won't. Get rid of that. Rho to the 0 power would just be 1, right? Rho to the 0 power. So it's C0, that constant. Well, rho to the 0 power is just 1, plus rho to the first power, and I should pre-multiply by a constant C1, plus the next constant C2 times rho squared, I guess, and I can just keep going on these all the way up, okay? And C3, rho to the 3rd power, and so on. Okay, so that's what we're talking about for V here, which is that guy. Well, it's a differential equation. I need the derivative right there. And then if you notice, the derivative is both multiplied by rho and multiplied by 1, and then, of course, with a constant. And so I need the derivative of that assumed solution with respect to rho. And then I'm also going to need rho times the derivative of that assumed solution with respect to rho. One of them will substitute in for that, and one will substitute in when you're multiplying that derivative by 1. Okay, well, you can see, I guess, that I also need the second derivative. Actually, what I really need is the second derivative multiplied by rho. So I've told you what this guy was, and I've told you what I guess this guy is, and hopefully that makes sense to you. I just bring down the j, and then c sub j, and then I subtract 1 from j right there. And when I multiplied by rho, well, I just multiplied by rho, and you can see it goes from j minus 1 to j. Now, one thing that is a trick to this, I guess, in these series solutions is you want to reorient so that everything has the same power of j. Okay, and see what I've done here. I've let j go to j plus 1, which is legitimate, I guess. I'm just going to have when j is equal to 0, it'll just kind of go away. But now I've got the same power, so I can equate equal powers of rho. That may or may not make sense to you, but when you, I guess here's the point. If I went 3, and I'm not going to go rho, I'm going to go x plus 7x squared plus 5x cubed. And then I said that's equal to ax plus bx squared plus cx cubed. If I had those two polynomials equated, hopefully you realize that a has to be equal to 3 here, regardless of what b is. B has to be equal to 7. C has to be equal to 5. And so if you've got a series solution and you're plugging these in for v, the derivative of v, and the second derivative of v multiplied by the appropriate variable here, just to change things, if you're going to set those all equal to 0, well, that would mean that all the individual coefficients of the terms, when you're looking at the coefficients of the same power of rho, they all have to be equated. And the only way you can do that logically is to get the same power, j, in each case. Hopefully I said that so it made sense. In fact, if I didn't have these two, if I had a whole bunch of things over here set up to be a whole bunch of things here, I would go 5 minus c times x cubed has to be equal to 0, and it has to be equal to 0 along with 7 minus bx squared. Each of these things individually would have to be equal to 0 to have the thing equal to 0. And so all the coefficients of the same power have to be 0. And that's what we're doing by making this step from j, where my power of rho is j minus 1. I need to transform it so that they all have the same power of rho, just like these had the same power of x here. Okay, so you have to work through that. And tutorial 7 through 12 steps, I think, does a nice job of forcing that through to you. And then I guess the point is, you notice this c sub j minus or j plus 1 right here. It can be manipulated so that you can get all the other terms that are in the coefficients, and then you'll have the other ones will all have this c sub j, and you can find a relationship between two adjacent coefficients here, the next one up and the previous one. And this is called a recursion relationship. So if I know what C1 is, I can figure out what C2 is. If I know what C0 is, I can figure out what C1 is, and so on, right? I can figure out what all these coefficients were, assuming I know the next one below. And all of this starts at C0. C0 is going to be my undetermined coefficient that ultimately I'll find by normalization. And then if I know what C0 is, I can figure out what C1 is, assuming I know all these things, okay? I know what J is. And oddly enough, L, the angular momentum number from the angular solution, the spherical harmonic solution, comes in and plays here. And I still have that, remember that big grouping of constants, rho 0. So this is a real important step in any power series solution to a differential equation, is achieving this thing called a recursion relationship, which tells you how to find the coefficients in your series solution. And of course, you know what the thing it's multiplied by is. It's just in this case, rho squared, rho to the first, and all the way up to rho to the infinity. And how many terms you've got? Well, that's how many do you need? Except, and here's an except. That series solution I just talked about, it is part of V, and V is part of U, and U is part of, I hope I wasn't breaking up too badly there. V is part of U with some things multiplied on it. And then U is part of R, I guess with something divided away. And R is the radial part of the wave function, psi. And this has to be normalized, which really is another way of saying that this series right here, it has to truncate. I mean, you can't just keep adding terms that are higher powers of J forever. At some point, there has to be a coefficient that goes to 0, and all the higher coefficients, maybe it's C2 goes to 0, and C3 goes to 0, and C4 goes to 0. Otherwise, V and U and R would not be normalizable. They wouldn't live in Hilbert space. They wouldn't be L2, as the mathematicians like to say. So we have to accept that there is going to be a point where, I might have a C1, but C2 goes to be 0. And then C3 would go to 0, C4 would go to 0. And so I guess the solution for V would only have a C0 and a C1 in this case. Well, how could that possibly happen? Well, hopefully you can see in this recursion relationship, the way that would happen is if the numerator goes to 0, right? Now, how does the numerator go to 0? Well, I guess that has to be equal to 0. We're going to define, and it works out quite nicely, that this grouping of all the terms we had, rho 0, remember what that was back a couple slides? It was a bunch of constants, right? And I do want to point out the significance of this. Kappa here was that grouping of constants, okay? And the big term in all of this was our energy eigenvalue, wasn't it? So rho 0 is related to energy through kappa. And so hopefully we can see right here that by making this definition that this rho 0 is related to kappa, this rho 0 is also related to energy. And we're saying that energy is directly related to this grouping of constants we're calling N, right? Okay, and so that's, we picked 2N because it just kind of works out real nice. All right, so I guess that is an important number because that determines where our series truncates. And I think we've just, through this constant, said, well, there must be different values of E depending on what the value of this N is. And we'll see in a second here as I work through it. But this should be pretty familiar to you because this is where Borg model comes in and melds into this kind of Schrodinger wave equation, and the two things kind of come together for us. Because if what I said is true, solve for this energy eigenvalue right here, okay, get kappa, plug it back in there, and you get this. You can do the algebra on your own if you'd like, but you can trust me on it. Hopefully I didn't make a typo here. The textbook likes to call Coulomb's constant 1 over 4 pi epsilon 0. And I'll throw that at you if you want periodically on my slides, but I'm too lazy to put in 1 over 4 pi epsilon 0. So I write Coulomb's constant K. Just make sure you can see it's different from that kappa constant that's related to the energy. So it's in the exponent of our solutions too. So just so you know what I'm doing right there. And once you make this substitution, you can see that this energy eigenvalue N is inversely proportional because of the square root to this N squared, right? And so what I did is I brought all those constant together. You can see that some of them cancel, right? That's h bar to the 4th and h bar squared here. That's mass to the 2nd power, and there's mass here. And so a lot of these things cancel. It does simplify nicely. The energy eigenvalue is proportional to 1 over n squared. And if you put in numeric values for the mass of an electron, the charge on an electron, Coulomb's constant, h bar, Planck's constant, divided by 2 pi. Well, I'm hoping that we all did this last semester in modern physics, or 2 semesters ago for those of you at Gamble. And you know that number is 13.6 eV when you put in the right constants with a negative sign because it's still there. all originating right there from that. And of course, that is the Bohr model's energy for this electron in the hydrogen atom. And we draw it something like this. So minus 13.6, then you divide by 2 squared minus 3.4, and so on. Okay. And people even like to group constants even better, I guess, because remember we said rho was kappa r, and then I just decided that, I guess, is it obvious what I did right there? It turns out that if that kappa can be solved for this thing, which is 1 over n times a, and that was the brilliance of making this substitution for rho 0. It just means that rho is r divided by this a n, and we define a to be what we called all these other constants. That's the Bohr radius, and it's about a half an angstrom. 0.529 times 10 to the minus 10th angstrom. Again, we're linking in a lot of Bohr model modern physics to quantum mechanics and a solution to the radial portion of the wave function, okay? Except we're twice removed from the radial function because we went through a substitution variable u, and now we're finding a substitution variable r. We're using a power series solution and paying attention to the recursion relationship and what pops out if you make the right definition for what this rho 0 was, 2 times this thing, which hopefully you recognize as the principal quantum number, well, you get the Bohr model. And that's just, it's great, I guess. All right, but let's put the eigenvalue back together. We've talked enough about modern physics stuff, hopefully you already know. Remember from 2 days ago, I guess, spherical harmonics, that's still part of what we're doing here. And we now need to stitch back together, since we know the recursion relationship and we've got an expression for V, and we know that things are going to truncate in this series solution for V based on this recursion relationship. And you can see I substituted n right here for rho 0, and I lumped it in with the 2 because 2n is rho 0. And I want to think about a couple cases here. And I hope I've just, all the things we've redefined, I've put in here. Remember, this is U, which now is just the V we just figured out how to solve for. The things we're going to, the asymptotic solutions we're going to multiply together. And of course, that brings us back to get R right there. Okay. And so that's the whole point of this. But I wanted to make sure it's all visible for everybody. And so now let's try to write R, which is U over R. And I got this guy. And of course, I need to substitute that away because we're half in rho and half in R here. So that's a little bit of a problem. But let's think about that lowest state that we had from the Bohr model that came out of all this recursion relationship, this minus 13.6 divided by 1 state, the lowest state down here. Let's think about what that has to have. Oops, wrong way, sorry. If n is equal to 1, we call that the ground state, and there must be a maximum value on J right here that is 0. And if you look, if J is equal to 0, and if there's any J above that maximum value, well, we want the series that is V here to truncate beyond that. And for the lowest state, you would figure J would be 0, so J max in this case is 0. Look what happens. I have J equal to 0. That must, I guess, mean that's also 0. So I got 0 and 0 right here. And then there's a 1 naturally from the recursion relationship. We said this is the ground state, which we're going to make 1 is equal to 1. I got 1 minus 1. If I start off with C0 then, and then I need a C1, well, you can see right away, C1 doesn't exist. And this series truncates after just one term, C0, because C1 is going to be 0 based on what is going on in the numerator of the recursion relationship. And that's what you would want to happen for the lowest state, okay? And so I guess immediately we know what this guy is. This V function is just C1, okay? And we've decided for this n equals 1 state, the lowest state, it had to be L equals 0 to work out here. And if you remember what we talked about when we talked about spherical harmonics, if L is equal to 0, well, that must mean that M is equal to 0. So all of a sudden, these numbers M, which we talked about for the phi equation, right, in the spherical harmonic Y equation, and L, which was critical in the theta equation, and N, which we're now introducing in the radial equation from the power series solution, okay, and this redefining of a couple constants, they link together a particular state. N equals 1, L equals 0, M equals 0, and of course those are called the quantum numbers. All right, so for this lowest state, let's construct what V is, and I think I said it, but I'm writing it out right there. It only has one term because it truncates beyond there, and by truncating, I mean this recursion relationship. The numerator goes to 0, so the next coefficient up must be 0 above C0, okay? And then that means, I guess, that R10 here is, and it's just the piece I'm going to write right here, but it does give me some specificity there. I can only find in this lowest state N equals 1, L equals 0, and that is my pattern, right? My pattern is I'm going to have NL, and that means I can only have this L equals 0, M equals 0, Y, which if you go back and look or pull it up on a chart is just that, is what we decided, because that's how we said the Y function is defined. And R10 here, let's see, must be 1 over R, rho to the 0th power. I'm sorry, 0 plus 1. So just rho, which becomes R over A, because that's what rho is when N is equal to 1. N is equal to 1. And it's to the first power, because L is equal to 0. And then let's see, from this piece right here, I took care of that piece. I took care of the 1 over R. From this piece right here, I get E to the minus R over A. Don't forget what A is. A is the Bohr radius. It's just a grouping of constants. But boy, it would be a pain in the butt to put those constants right here and right here. And simplifying that, I guess, that out of my way a little bit, I got C0 over the Bohr radius times E to the minus RA. Okay, and I'm running out of time, so the last thing I want to do on this ground state here, this minus 13.6 energy state, is I want to normalize it and just see what that C0 is. And so I got that guy, right, already taken care of. We left off here, and we haven't normalized C0, so I'm going to put it in the R squared, little r squared dr, jammed out, brought the coefficients out front, and I wrote it as C0 could be complex, I don't know, so I wrote it as its amplitude squared, and then I was just left integrating this R squared dr. I used this integral lookup to do it, okay, and in that integral lookup, I guess alpha becomes A over 2, doesn't it? Because in this alpha right here becomes A over 2, and I'm doing a case where N is equal to 2, and so I just bring the coefficients out. It goes to N plus 1, right? N plus 1. 2 factorial is just 2. It looks like I got A over 4 here when I cancel everything, because there's a cubed, that makes it 8 times 2, 4, cubed over squared becomes A, yep. And so that tells me the value of C0 must just be the square root of 4 over A, and that's why I said that right there. And so that must be the normalization constant that I'm going to put right here, okay? And let's see, where'd the other A come from? Well, right there, I guess, right? Okay, so there's the other A, and then the exponent. If I put it all together, the ground state then has the square root of 1 over 4 pi. It has that guy right there, the radial part, and I just simplified it, and that must be the wave function for the ground state. And I think I'm going to call it a day right there. That gets you, if you can get all the way through all of that, that does absolutely get you through to the end of the tutorial that's titled hydrogen atom, I guess hydrogen atom 1. And we'll pick up with a hydrogen atom 2. And I'm going to go to the next state up, the N equals 2 case, come Monday. Okay? Wow, that's a lot of math, a lot of looking at the results of the mathematics to draw conclusions. And we'll finish up some more on that and pick it up with higher states, and then some kind of pulling it all together into some of the work by Laguerre on Monday. Hey, that's what I got. I'll jump out of here, hopefully. Oops, how many states? We'll talk about that next week. All right. And I guess unless we got any questions, come on, you can do it. Stop the share. We'll call it a day here. And I will be setting up office hours, 3 o'clock today, normal time, for anybody who has questions on the spherical harmonics tutorial. And I see people are bailing out, so you guys have a great weekend. Enjoy.